Whenever you ask an AI a question or get it to generate an image, you're tapping into something, well, it's just unimaginably huge. But behind all that digital magic, there's a very real, very physical world of massive, power-hungry infrastructure. So today, we're going to pull back the curtain on the secret weapon Google built to solve a problem that honestly could have sunk its entire AI strategy. And trust me, it's about way more than just a single chip.
So picture this, it's 2013 and Google is staring down the barrel of a crisis. The AI they were pioneering, things like voice search, was becoming so popular that their projections showed they would literally have to double the size of their data centers just to keep up. And as this quote puts it, that would be very expensive. I mean, that's a bit of an understatement, right? This wasn't just some small hurdle. This was a potential company killer.
So what do you do when the technology you're creating threatens the very economics of your business? How do you even begin to solve that? Do you just keep building more of the same stuff, only faster? Or do you have to rethink everything right from the ground up?
See, the challenge here wasn't just about raw speed. It was about cost, it was about power consumption, and it was about reliability, all at a scale that was just mind-boggling. The real problem was finding a whole new economic model for doing AI, one that wouldn't bankrupt the company as AI took over the world.
And this right here is the absolute key to the whole story. Google realized they couldn't just go out and buy faster off-the-shelf parts and hope for the best. The solution had to be, well, it had to be everything working together. They had to co-design it all, the silicon itself, the network that connects it, and the software that tells it what to do, so that every single piece was working in perfect harmony to solve their specific AI problems.
All right, so let's dig in, and we'll start at the foundation, the chip. This is probably the most famous part of the story, but believe me, it is only the beginning. They didn't just try to make a faster version of what was already out there. They built a highly specialized engine for one very, very specific job.
And that engine is the Tensor Processing Unit, or TPU. It's a custom ASIC, which basically just means the chip designed for one specific application. Unlike a GPU in your gaming PC that has to be a jack of all trades, the TPU was built with this laser-like focus to just crush the massive matrix math that is the absolute lifeblood of every neural network.
So how in the world does the TPU get to be so fast at this one thing? Well, the secret sauce is a really cool concept called a systolic array. Just try to imagine this huge grid, thousands and thousands of tiny, simple calculators. And the data from the neural network, it just flows through this grid in this perfectly synchronized rhythmic pulse, almost like a wave. Each little calculator does its one simple job and passes the result to its neighbor. It is an unbelievably efficient assembly line for crunching giant matrices.
And this really shows you two completely different ways of thinking about chip design. A GPU, on the one hand, is like a flexible Swiss Army knife. It's got thousands of general-purpose cores and complex memory caches managed by the hardware. But a TPU? It's more like a specialized wrench, built for one job. It uses fewer but way more powerful cores. And instead of complex caches, it relies on these big, compiler-managed scratch pads. Think of them like perfectly organized workbenches set up ahead of time. It's a trade-off, for sure. You give up flexibility to get just extreme efficiency.
Okay, but what happens when the data isn't a nice, neat, dense grid? A huge part of Google's work, like the recommendation models, relies on these enormous but mostly empty, or sparse, tables. That kind of data is a terrible fit for that main matrix engine we just talked about. So, what did Google do? They built another specialized unit right on the chip, called the SparseCore. It's a processor dedicated to handling just this one kind of data. And the results are just staggering. A 5 to 7 times speed up, while only taking up about 5% of the chip's space and power. It's another perfect example of just how powerful that specialization can be.
Okay, so you've designed this ridiculously efficient chip. Great. But how do you connect thousands of them together to train one single gigantic AI model? This is where we go from a single chip to the entire system. And honestly, this is where Google's real advantage starts to become crystal clear.
So the chips are all connected in what's called a 3D torus. The absolute easiest way to picture this is as a giant three-dimensional donut. Seriously, every single chip is connected directly to its 6 closest neighbors, up, down, left, right, front, and back.
And this design creates this incredibly dense fabric where messages can get from A to B through very short, direct paths.
But here is the real magic, the secret ingredient that makes this whole thing work at an insane scale. It's not just the shape of the network, it's how the connections are physically made. Google uses these custom-built optical circuit switches, or OCS. Instead of complex, power-hungry electronics, these things use tiny mirrors to literally steer beams of light, creating direct optical connections between any two parts of the supercomputer.
And the benefits of doing it this way are just immense. The OCS is what lets them connect over 4,000 chips into one giant machine. It gives them incredible reliability. If a chip or even a whole rack goes down, the OCS can just reroute the light around the problem on the fly, no big deal. It lets them carve out slices of the supercomputer in any shape or size they need for a particular job. This isn't just a networking trick, it's a true system-level superpower.
And because this optical network is reconfigurable, it's not static. This is where it gets really mind-bending. Google's software can dynamically rewire the entire network for a specific job. They can create something they call a twisted torus, which basically programs in long-range shortcuts across the donut. For certain jobs that require a ton of communication, this simple change, just rerouting the light, can make the whole thing run up to 1.6 times faster.
All right, so let's put all the pieces together and see what kind of a monster they've actually built. When you combine that specialized chip with this incredible reconfigurable optical network, well, the results are pretty amazing.
So here's how the scale builds up. It starts with 4 liquid-cooled TPU chips on a single board. Then you pack 16 of those boards into a rack, which gives you a cube of 64 chips. And then, using those optical switches we talked about, you connect 64 of those racks together to create a full 4,096 chip superpod.
And here is the payoff. This is what all that effort gets you. Based on industry-standard benchmarks, the TPU-4 system is, on average, somewhere between 1.2 to 1.7 times faster than a comparable top-of-the-line system from NVIDIA. But, and this is the huge part, look at the power. It uses 1.3 to 1.9 times less power to get that speed. That performance per watt advantage is the direct result of that obsessive, co-designed approach.
Now check this out. When Google was training its gigantic Palm language model, a job that ran nonstop for over 50 days, they needed to squeeze every last drop of performance out of the hardware. The sustained performance they achieved was 57.8% of the theoretical peak. Now that number might not seem huge at first glance, but in the world of high-performance computing, to sustain that level of efficiency at that scale for that long, it's almost unheard of. But the real takeaway from that number isn't just about speed. It's about extreme reliability. The only reason they could possibly get that kind of sustained performance is because the system as a whole is incredibly resilient. During that 50-day marathon, chips failed. They always do. But the optical circuit switch network just routed around them, keeping the whole job running without a single hiccup. That right there is the system proving its worth in the real world.
So let's just zoom out one last time to really lock in what the real secret weapon is here. Because it's not any single one of these components. It's about how they all fit together like a perfect puzzle.
The true innovation, the real secret, is this deep co-design of 3 pillars. You have the specialized hardware, with things like the Tensor core and the SparseCore. You have that revolutionary reconfigurable optical network. And then you have the software, the XLA compiler, that knows this specific hardware and this specific network inside and out so it can optimize the code before it even runs to make the absolute most efficient use of every single resource.
And the whole philosophy behind it all was perfectly captured by the TPU's lead architect way back in 2017. He called it the cornucopia corollary. The big idea is that if you can build a massive, specialized resource really cost-effectively, it can deliver incredible performance, even if it isn't running at 100% all the time. It's a shift in thinking. You build for abundance and efficiency, not just for raw peak speed. And this all brings us to a really fascinating and kind of huge final question. Google's approach proves the incredible power you get when you tailor your entire computing stack from the silicon all the way up to the software for your specific problems.
So does this mean the era of general-purpose computing is fading, at least for high-end AI? Are we moving into a future where every major tech company is going to have to become its own chip designer and systems architect just to stay in the game? It's a pretty provocative thought, and it's one that's definitely going to shape the next decade of technology.